Hi, let's have class. Besides auto-encoder for different downstream tasks, I also want to talk about how auto-encoder is used for other interesting applications. I will talk about feature disentanglement. What is feature disentanglement? Or, what is disentanglement? Disentanglement is to separate things that have become joined or confused. This is called disentanglement. Then, why do we study feature disentanglement? Let's first think about what auto-encoder does. An auto-encoder turns an image, for example, into a code, and then recovers the image from the code. Since the image can be recovered from the code, it means that the code contains a lot of information, or contains all the information of an image. For example, important information of an image, such as color and texture, and so on. Besides the image, auto-encoder can also be used in speech processing. You can input a segment of utterance into the encoder to obtain a vector and then recover the original input with the help of the decoder. That vector contains all the important information in the utterance, including linguistic information of the utterance, or we called it content, as well as who spoken the utterance. We called it the speaker information. For text, if we input an article into the encoder for a vector, the decoder recovers the original article with that vector. What may be in this vector? There may be the syntactic information of the article, and semantic information as well. However, these pieces of information are all entangled in a single vector. We do not know what exactly is in a specific dimension of a vector. For example, if we input a segment of an utterance to the encoder, it gives a single vector. However, in this vector, which dimensions are for the content of the utterance? Which dimensions for the speaker information? We do not know. Feature disentanglement is thus a solution. When training an auto-encoder, we would like to figure out that for a representation, or an embedding, or code. These are just the same thing. What information is encoded in a specific dimension? Is it possible to make the encoder output, for example, a 100-dimensional vector, where the first 50 dimensions are for the content of the utterance, while the last 50 dimensions are for the speaker information? Such a technique is called feature disentanglement. Actually, there are many kinds of approaches to achieving feature disentanglement. I wanted to talk about the details of these approaches, but I think it is okay to skip this for now. In this part, we are just telling you feature disentanglement is feasible. As for how it is achieved, I will list a few papers here, so whoever is interested can refer to them. If you have no interest in them, you can just believe that feature disentangle is feasible. The chances are that we can probe the information encoded in each dimension of the auto-encoder. Okay, what are the applications of the feature disentangle? Of course, you can think about what kind of applications are there. There is a speech application that utilizes feature disentangle. This application is called voice conversion. What is voice conversion? Voice conversion is called Yuyin Juan Huan in Chinese. You may not hear voice conversion before. However, you must have seen its application. It's Conan's voice-changing bowtie, which is invented by Dr. Ali 20 years ago. In the past, he needed paired voice signals for the voice conversion. In other words, suppose you want to convert the voice of A into the voice of B. You must find both A and B. Then, ask them to say exactly the same sentences. A says, "How are you?" And B says, "How are you?" as well. A says, "Good morning." And B says, "Good morning," too. They have to say exactly the same sentences. Suppose we have 1,000 sentences that said by A and B. What is next? It's nicely done. It is a supervised learning problem. You have paired data so that you can train a supervised model. Your model takes A's voice as input and produces B's voice. It's over. However, it is unrealistic to ask A and B to say a lot of sentences. For example, I want to convert my voice into that of Yui Aragaki. I have to bring Yui Aragaki here. To say the least, even if I really bring her here, she can't speak Chinese. Accordingly, she can't say exactly the same sentences as I do. However, our machine may be more powerful. With the feature disentangle technology, we can just give it the voice of A and give it the voice of B. And A and B don't need to say the same sentence. They don't even need to speak the same language. The machine may also learn how to transfer the sound of A into the sound of B. How is it actually done? Suppose we collect a lot of human voices. Then we utilize these voices to train an autoencoder. At the same time, we perform the feature disentangle in the autoencoder. So we can know which dimensions of the output of the encoder encode the content of the voice, and which dimensions encode the characteristics of the speaker. In addition, we can perform the voice conversion. How do we do it? We already know the parts representing content information, and the parts representing speaker characteristics, in the latent of the encoder. Followingly, we can swap the content information and speaker information of the two voices. For example, here I say, "How are you?" After feeding it into the encoder, we can get some information. In this encoder, we know that some dimensions represent the content of, "How are you?" and some dimensions represent my speaker characteristics. If you feed the voice of your wife into the encoder, it knows certain dimensions represent what your wife said, while certain dimensions represent the characteristics of your wife's voice. We just need to take out the content that I said and extract the voice feature of your wife, concatenate them together, fed it into the decoder. Then, we will have an utterance of your wife saying the content, "How are you?" Is this really possible? The following is a real example. It sounds like this. Do you want to study for a PhD? Okay, so this is my voice asking if you want to study PhD. Oh, by the way, in this course, I will keep encouraging you to study PhD unawares. Okay, let's come back here. After feeding my utterance into the encoder, you can imagine that in the encoder, we know which dimensions represent the content, and which dimensions represent my voice. For simplicity, just imagine that the encoder outputs a 100-dimensional vector. The first 50 dimensions represent the content, and the last 50 dimensions represent the characteristics of the speaker. Next, there is another sentence said by your wife. I'm not sure what she is talking about. It's Japanese. We feed this utterance into the encoder. Similarly, the first 50 dimensions represent the content, and the last 50 dimensions represent the characteristics of your wife's voice. And then, take out the first 50 dimensions of my utterance, which is the part of the content. As for your wife's utterance, feed it into the encoder, and extract the last 50 dimensions. Concatenate them to become a 100-dimensional vector. Feed it into the decoder. Take a look at the output utterance. Is it actually your wife saying, "Do you want to study for a PhD?" In fact, it sounds like this. Do you want to study for a PhD? Did you hear that? Now you should rush into applying to a doctoral program. Furthermore, we can actually do it conversely. Take out the content of the Japanese, and then extract the characteristics of my voice. Concatenate them together into a 100-dimensional vector. Feed it into the decoder. It sounds like this. I don't know what I'm talking about. Okay. Overall, it is possible to do voice conversion by using feature disentangle. Besides, no matter whether in the computer vision domain or the NLP domain, we can adopt the same approach. Hence, you can think about what feature disentangle can do. Okay, the next topic I want to tell you is called discrete latent representation. So far, we have assumed that the embedding is a vector. We have a string of numbers here, which is, specifically, real numbers. However, can it be something else? For example, can it be a binary number? What are the benefits of using a binary number? One of the benefits is that every dimension of the embedding can represent the presence or absence of a certain characteristic. For example, if the input is an image of a girl, then we will have the first dimension to be 1. As for a boy, the first dimension is 0. If you wear glasses, the third dimension will be 1. If you don't wear glasses, the third dimension will be 0. We simplify the embedding by setting all dimensions in the embedding as binary. All dimensions in the embedding become a number with only 0 and 1. We can explain the embedding easier with simplification. Is it possible that make the vector becomes a one-hot vector? Only one dimension is 1. and the others are 0. We force the embedding to be a one-hot vector. That is, input a picture into the encoder. You will obtain an embedding in which only one dimension can be 1, and the others are 0. What kind of effect can it achieve? It may achieve unsupervised classification. For example, you want to train a classifier to recognize the handwritten number. Suppose you have a lot of pictures from 0 to 9 without labels. You can use all the pictures to train an autoencoder. You force the latent representation. In the middle of the autoencoder must be a one-hot vector. And you set the dimension of the latent representation as exactly 10. There are 10 possible in this 10 dimensions latent representation. Maybe every dimension in the latent representation will correspond to a number. If you use a one-hot vector as your embedding, the machine may learn how to classify without label data. Let the machine automatically learn to classify. Many other technologies also use discrete representation. One of the most well-known is VQVAE, which is Vector Quantized Variational Autoencoder. How does VQVAE work? You input a picture into the encoder and output a vector. In a common case, the vector is continuous. Then, you have a row of vectors which we call codebook. You can make the model learn the code by itself. You calculate the similarity between the output of the encoder with all vectors in the codebook. You maybe notice that we only calculate the similarity. You will find it is similar to calculating self-attention, right? The output of the encoder is a query. And these vectors are keys. It's very similar to self-attention. When we spoke about self-attention, we spend a lot of effort explaining query, key, and value. So this is the query. This is key. Next, let's look for which vector in the codebook is the most similar to the output of the encoder. Then you take out the vector which is most similar to the query. In the VQVAE, the keys and values share the same vectors. If you use self-attention as a metaphor, it means the key and value are the same. Input the vector into the decoder. Then, make the decoder output a picture you want. During training, we want to make the input to output as close as possible. This decoder, this encoder, and this codebook are all learned from the data. The advantage of doing this is that you can have a discrete latent representation. That is to say, the input of the decoder here must be one of the vectors in the codebook here. We assume there are 32 vectors in your codebook. The input of your decoder could only have 32 possibilities. It's like that you make your embedding discrete, and not having endless possibilities. It only has 32 possibilities. Actually, for a technology like this, if you apply it to voice, you just input a voice signal through the encoder to generate a vector. What's next? You calculate this similarity and select the most similar vector to throw into the decoder to output the same voice signal. At this time, you will realize that your codebook may be able to learn the most basic parts of pronunciation. For example, the most basic unit of pronunciation, which is also called phonetic. If you don't know what phonetic is, you could think of the KK phonetic transcription. Then, you will realize that each vector in this codebook corresponds to a certain pronunciation and a certain symbol in the KK phonetic transcription. This is VQVAE. There are actually more crazy ideas. Does representation have to be a vector? Can it be something else? For example, can it be a piece of text? Yes, it can. For example, we are going to do an autoencoder of text. In text, the concept of autoencoder is not different from the concept in audio or video. That is, you have an encoder, and you throw an article in it. It may generate a vector. Then, you throw this vector to the decoder to reconstruct the original article. But, can we not use vectors as embedding now? Can we say our embedding is a string of text? If we turn embedding into a string of text, what are the benefits? Maybe, this string of text is the abstract of the article. Because you can think about it. You throw an article into the encoder, and it outputs a string of text. By using this string of text, you can reconstruct the original article through the decoder. It means this text is the essence of this article. Which is the most critical content of this article? That is to say, it is the abstract of this article. However, the encoder here needs to be a sequence-to-sequence model, obviously. For example, transformer. Because our input here is an article, and the output here is a string of text. The decoder input is a string of text, and the output is an article. So, it's all about inputting a sequence of things, and outputting a sequence of things. It's all about inputting a sequence of words and outputting a sequence of words. So, the encoder and the decoder must be a sequence-to-sequence model, obviously. So you can imagine that this is a transformer you trained for homework 5. This is also another transformer. Both of them read a piece of text and output another piece of text. So this whole autoencoder is not an ordinary autoencoder. It is a sequence-to-sequence-to-sequence autoencoder. It turns a long sequence into a short sequence, then restores the short sequence back to the long sequence. And when this autoencoder is training, data does not need to be labeled, because training an autoencoder only requires lots of documents. You only need lots of unlabeled data. In this case, lots of documents will do. If you can successfully train this model, if this string of text can really be the summary, you have enabled the machine to learn to do summarization automatically. The machine has learned to do unsupervised summarization automatically. But is it really that easy? In fact, when you start training, you'll find that this won't work. Why? Because the encoder and the decoder will invent their own secret code. So it will generate a piece of text, which you can't understand. You can't read the text, but the decoder can understand and restore the original article. But since people can't understand, it's not a summary at all. How do we solve this? We can apply the concept of GAN by adding a discriminator. The discriminator has read sentences written by people, so it knows what sentences written by people look like. These sentences don't need to be the abstracts of these articles. They can be another bunch of sentences. So it knows what sentences written by people look like. And then, this encoder must find a way to fool the discriminator. The encoder must find a way to generate a sentence that can not only be used by the decoder to restore the original document, but also let the discriminator feels like it's a sentence written by a human. We expect by using this method, we can force the encoder to generate a summary that people can understand, instead of some cryptic text. Then you might ask, how to train this network? This output is a string of text. How to connect this text to the discriminator and the decoder? I'll tell you. When you see a problem that you can't train, just use RL to do it. So here you use RL, and it's over. Okay, so, after the network has been trained, you might feel this concept is a bit like cycle GAN. Indeed, you can think of this as a cycle GAN, where this is a generator, this is another generator, and this is a discriminator. You want the input and output to be as close as possible. This is essentially a cycle GAN. We are just looking at the idea of cycle GAN from an autoencoder point of view. Okay, what is the actual result? The following is the output of the real network. You give it an article to read, and it uses the autoencoder way to train for 3 million articles. Then you give it a new article, and see if the encoder's output is a human-readable summary. For example, if we show this article to the encoder, the output is Australia strengthens drug testing outside of sports competitions, which looks fine. Here's a more remarkable example. The article is about the Chinese Taipei Olympic Committee receiving an invitation letter for the 1992 Winter Olympics that day. After passing the article to the encoder, it outputs the CTOC received Winter Olympics invitation. It somehow learned the abbreviation of the organization, which is CTOC. For some unknown reason, it picked up this knowledge by itself. Of course, a lot of times, it still makes mistakes. I especially like the ridiculously wrong examples. For example, if you input the article about the rain that's been going on for days in the Indonesian island of Sumatra, what will the machine's output be? The output of the encoder is flooding in Indonesia Sumatra. What does Indonesia Sumatra mean? Perhaps it is the abbreviation of Indonesian island of Sumatra. Maybe in the sentences written by humans. Abbreviations like that appear quite often. to the point that the encoder feels like Indonesian island of Sumatra, can be abbreviated to Indone Sumatra. Sometimes it produces inexplicable sentences. For example, after passing this article to the machine, the output of the encoder is Hafez leading cadres at the grassroots level do business, welcome and send to the regulations. Although it does resemble the structure of a sentence, the content is total gibberish. So, this example is just here to illustrate that it is totally possible to take a piece of text as embedding. In fact, there are even crazier cases. I've seen someone take the tree structure as embedding. Someone turned a piece of text into a tree structure and used the tree structure to restore a paragraph of text. I've listed the references here in case you're interested. Next, we'll talk about more applications of autoencoders. What else can the autoencoder do? For example, the examples we've mentioned so far have been using the encoder. In fact, the decoder is also quite useful. If we single out the decoder, isn't it some kind of generator? Don't generators take a vector as the input and output something, like an image? Isn't that exactly what the decoder does? So, the decoder can also be used as a generator. We can sample from a known distribution, a Gaussian distribution, for example. We can sample a vector, pass it to the decoder, and see if it can output an image. In fact, back when we were talking about the generative model, we mentioned that in addition to GAN, there are two other generative models. One of them is called VAE, which stands for Variational Autoencoder. Judging from the name, it is obvious that it is related to the autoencoder. It actually takes out the decoder of an autoencoder and uses it as a generator. While there are, of course, other implementation details and techniques that made it possible, I'll leave it for you to look it up. So you are given a decoder after training the autoencoder. Autoencoder can also be used for data compression. As you already know, technologies such as JPEG compression compress the data when the data size is too big. Autoencoder can also be used for data compression. It is perfectly fine to take the output of the encoder as the result of compression. A picture is originally a very high-dimensional vector. Usually, the output of the encoder is a low-dimensional vector. Thus you can take that vector as the result of compression. So the encoder compresses the data, and the decoder decompresses it. But this compression method is lossy. That is, the compression results in distortion, because it is impossible to exactly recover the input image from the output image while training the encoder. So there will be a loss of information. Therefore, the compression technology using the autoencoder inevitably results in distortion, just like JPEG images. Autoencoder compression suffers from the same problem. Okay, now we are going to talk about a technique used in your homework. In the assignment, we will use autoencoder to do anomaly detection. Originally, I just wanted you to use autoencoder once in your homework. Out of many technologies related to it, I chose anomaly detection because it is a technique that can be applied in many different scenarios. Let's talk about the task. Suppose you are given a large amount of training data, labeled as x1 to xn. For better understanding, anomaly detection is usually translated to finding irregularities in Chinese. In this task, we are given some new data, and you have to answer the following question. Is it similar to the data you had seen before? More specifically, the goal is to train an anomaly detection system. It is trained with a large amount of data. Given a new piece of data, if it is similar to the previous dataset, the new piece of data is called normal. If it doesn't look like the previous dataset, the new piece of data is called abnormal. Actually, there are many other words that can replace the word anomaly. For example, outlier, novelty, or exceptions all refer to the same thing. The main goal is to determine whether a new piece of data is similar to the data it had seen before. But similarity does not have a well-defined definition. The criterion may vary depending on the application. For example, if the training data contains only Raichu, then Pikachu might be considered an anomaly. But assuming that all animals in your training data are Pikachu, then Raichu is abnormal. So we don't say that something must be normal, or something must be abnormal. We don't say that something must be normal or abnormal. Whether it is normal or abnormal depends on what your training data look like. Assuming that your training data are Pokemon, then Raichu and Pikachu are normal. And maybe so do Digimon. Do you know Agumon? This should be Agumon, right? Agumon is abnormal. Okay, what kind of application does this anomaly detection have? For example, it can do fraud detection. Assuming that there are many credit card transaction records in your training data, and we can imagine most credit card transactions are normal. Then you take the normal transaction records to train an anomaly detection model. When a new transaction record comes in, you can let the machine help you judge whether it is normal or abnormal. So, the anomaly detection technique can be used for fraud detection. It can also be used for this intrusion detection of the network. For example, you have a lot of connection log data, and you believe most connections are normal. Their behaviors are normal. Most people are good people. You have collected a lot of normal connection records. When a new connection comes in, you can train an anomaly detection model with the normal connection in the past and use it to detect the new connection. Is it a normal connection or an abnormal connection? Is it offensive or a normal connection? It may also have applications in medicine. You have collected a lot of data on normal cells and use these data to train an anomaly detection model. When seeing a new cell, the model can know if this cell has mutations. Maybe there is a mutation, or it is a cancer cell, and so on. When it comes to this, some people might ask, can we treat anomaly detection as a problem of binary classification? You said you want to do fraud detection. You just collect a lot of normal credit card records and a bunch of fraudulent credit card records, and then you train a binary classifier. It's over. Just like this, isn't it? The most difficult is the data collection. The difficulty of this anomaly detection problem is the data collection. Usually, you have a better way to collect normal data. You are less likely to collect abnormal data. You may have a lot of records of credit card transactions, but most credit card transaction records may be normal. Abnormal data may be very little compared to normal data. There are even some abnormal data mixed in the normal data. You may be unable to detect it at all. So, in this kind of anomaly detection problem, we tend to assume that we have a lot of normal data, but we have almost no abnormal data. So, it is not a general classification problem. This classification problem is also called a one-class classification problem. That is, we only have one category of data. So how do you train a model? Because if you want to train a classifier, you have to have two types of data to train the classifier. If there is only one category of data, then what can we train? This is where auto-encoder comes in handy. For example, suppose we want to make a system now. This system is to detect a picture. For example, whether it is a real human face. Then you can find a lot of pictures that are all real human faces. Then we take the faces of these real people to train an auto-encoder. For example, this is a picture of your wife. You can say, this is my wife. Please remove the photo. This is a picture of your wife. Then you can use it to train an auto-encoder. After you train this auto-encoder, while testing, if the input is also your wife's picture, because it has seen such photos during training, it can be restored smoothly. You can calculate how much this photo changes after it passes through the encoder and the decoder. You can calculate the difference between this input photo and this output photo. If the difference is small enough that your decoder can smoothly restore the original photos, it represents this type of photo is seen during training. But on the other hand, suppose there is a photo that was not seen during training. For example, this is not a picture of a person at all. She is a human. She is the leader. The leader is Haruhi Suzumiya. But she is not a real person. She is an animated character. She is a character of 2 dimensions. For a picture of a 2-dimensional character, after inputting it into the encoder and the decoder, because this is something it hasn't seen. This is a photo it hasn't seen during training. Your decoder is difficult to restore it back. If you calculate the difference between input and output, and find that the difference is very big. That means, the input photo for the encoder now may be an abnormal situation. It may be a situation that has not been seen during training. So you can watch the loss of reconstruction. The quality of this reconstruction decides that when you are testing, whether you've seen the same type of photos during training. This is what we want everyone to do in homework. Okay, this anomaly detection is another subject. We don't have time to talk about it in class. Anomaly detection is not limited to auto-encoder technology. The auto-encoder technology is just one of many possible methods. We use it as the homework of auto-encoder because I believe you will have a lot of opportunities in the future to use anomaly detection technology. In fact, for a complete introduction to anomaly detection, we put the video of the past class here for your reference. Okay, the above is the part about auto-encoder. Before we ask the teaching assistant to talk about the homework, let's see if you have any questions you want to ask. Hey, do you have any questions? No? Okay, if there is no problem for the time being, then we will ask the teaching assistant to talk about the next assignment.